Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to 29th lecture of VLSI Interconnects course. We are in the 4th module and we are discussing coupling in interconnects. In the previous lecture, we derived the coupled voltage equations. We saw that for two identical interconnects we can define a common mode and differential mode voltage, which allows us to decouple the equations, and then we saw the steps involved in analyzing this decoupled interconnects. So, in this lecture we will continue with this discussion on two identical interconnects. We will see how signal on one interconnect affects the signal on the adjacent interconnects, which leads to crosstalk and timing it. So, let us get started. Here let us very quickly recap the three steps that we had seen in analysis of coupled interconnects. So, if I have two coupled interconnects, I am assuming identical interconnects are of resistance R and C, and I have a coupling capacitance Cc is also distributed in nature. For this, my voltages are governed by these two coupled equations. So, now if I have a scenario where my input to this signal Vi1 of t is equal to Vd1 ut, and the input to this second interconnect is Vi2 of t is equal to Vd2 ut. The task before me is to find out what is my Vout1 of t and my Vout2 of t. So, as a first step, let us decouple the voltages. So, we define common mode and differential mode voltages, common and differential mode voltages Vcm and Vdm, and if we define it like this, these two set of coupled equations reduce to these two simpler looking equations. Then, as at step 2, I solve these two sets of decoupled equations. So, these are now decoupled. So, here now the resistance is R and C. So, this is for let me write this as C plus 2 Cc. This is for common mode and this is for differential mode, because here the capacitance is C plus 2 Cc and for the common mode it is just C here. So, we then solve these equations, solve the equations for these two decoupled interconnects, and then as at step 3, transform back to V1 and V2. So, then again you have a coupled interconnect like this, and finally, your V1 you can get in terms of Vcm and Vdm. So, these are the three steps that we will be doing, and then we will see that what does this analysis of simple identical interconnects tell us about the crosstalk and timing jitters. So, once we have that insight, then we can extend the analysis to more complicated scenarios. So, what we will assume here is that my V in 1 of t is equal to V d1 ut and my V in 2 of t is equal to V d2 of ut. Now, as a first step I have to define the input voltage. So, what is the input to this, right? I have to first find out, right, what is my V in common mode. No, so let me stick to some color code. V in common mode and this is V in differential mode. From here then we will get what is my V out common mode and then V out differential mode, right. So, what is my V in common mode? It is the addition of these two voltages. So, my V in 1 is there is simply V d 1 ut plus V d 2 ut, and similarly my V in differential mode is V d 1 ut minus V d 2 ut. So, let me write this as V common mode as V d 1 plus V d 2 into ut. So, here in this analysis, in addition to the interconnects being identical, we are also making another assumption that both these voltage signals are sort of synchronized. So, this is ut and ut. We are not considering any u of t plus t naught or something like that, just to make it simple. So, there is this inherent assumption in our analysis when we are writing both the voltages on this form. So, this I can write as V d 1 minus V d 2 into ut, right. So, what I can also do is that for the case of common mode interconnect, I can write my transfer function something like this, and I can then do some approximation. So, I am doing an Elmore approximation where I am saying my h of common mode is approximately equal to 1 by this. So, this is like the dominant RC constant, and in our simulations also we had seen that if we take the Elmore delay, that for a single I mean an unbranched interconnect, that was coming very close to the 63% delay, and that is why we can say more or less, okay, this is the dominant delay. So, this is sort of one pole approximation which we did for Elmore analysis, right. So, here in this case this is my common mode interconnect, my resistance is R and my capacitance is C. So, in this case my common mode T d Elmore delay, right, my T d Elmore, this is T d common mode is, and the length here is L, is R C L square divided by 2, right. So, this is my approximate this is an approximation that I am making, right. This is transfer function. Now, if I substitute this transfer function and get the voltage, this is like you have an RC circuit, right, a single R dominant or RC dominant RC, right. So, your dominant RC. So, I can then, if this is my transfer function for input of this form, I will be getting my V out. So, this is my output, this is my V out Cm, my V in Cm of t is the input here. My output would be of this form, right, simple. So, this is my RC is replaced by TDCM, where TDCM is this. Similarly, for the case of differential mode interconnect, I can write my HS as H of S for differential mode as this. Again, this is a dominant mode approximation. Here the resistances are, but now the capacitance is C plus 2 Cc. The length is L. V in differential mode is my input and V out differential mode is my output, and my T d differential mode is R into C plus 2 Cc into L square divided by 2. So, for this case again I can get my V out differential mode as this. So, this is I am just simply using this. This is my input. So, whatever this was comes here, and then I have this RC type of behavior, right. So, now we have got the output voltages for the common mode and differential mode interconnects. Now, what we want to do is we have to transform them back. So, to transform them back, we will be using these two equations. So, if I want to V out of t, what I have is my, let me write in V out of common mode plus V out of differential mode divided by 2, and here I have V out of common mode minus V out of differential mode divided by 2. So, we are transforming back to physical voltage of V 1, V out t, and V out 1 and V out 2. So, now if I substitute these things here back, what will I be getting? So, if I substitute this is simply so there is half, right. This term here is, so this was this here. So, this is your V, or say V out common mode, and this term without by 2 is your V out differential mode. So, then if you solve it, you can then collect the terms of V 1. So, if I collect the terms of V 1 here, V d 1. So, in that case you will have half here. So, you will have a term of 1 here, then you multiply this here and multiply this thing here, there is a plus sign. So, there would be you can write this as minus of e to the power minus t divided by t d common mode plus e to the power minus t divided by t d differential mode, and this is now divided by 2. Then there is another term which is dependent on V d 2. So, here you can see your output voltage of interconnect 1 depends on the input or say the amplitude of the input voltage on the interconnect 2. So, you are getting this V d 2 term here. So, that V d 2 term will be there. Now, if I collect those terms of V d 2, what I will get? So, there is a minus sign here and minus sign here. So, I have taken minus sign out already. I will have e to the power minus t divided by t d common mode minus e to the power minus t divided by t d differential mode divided by 2. So, if I look at this, I would strongly recommend that you check this on your own. There would be a minus sign here. So, the first term is T d C m, that minus has come out. Then there is minus I have taken out. So, there is a minus term here again of T d minus t divided by T d d m, right. So, you have this term. Now, similarly for interconnect 2, similarly for for interconnect 2, you can get an equation of this form. So, for the second interconnect you have this equation. This also has a term of, so there is this term of VD1. So, your output voltage of interconnect 2 also depends on the voltage on interconnect 1, and then there is this term. So, now here you can see that this term would be the unwanted term, right. This term would be the unwanted term. Similarly, here in this case this term would be the unwanted term. So, this we can say is a crosstalk. So, if I look at it, the scenario is something like this. On the interconnect 1, I am giving an input signal like this. Okay. So, for this analysis, let us say that for the interconnect 1, I am not giving any signal, right. So, my VD1 is equal to 0, right. And then for the second interconnect, I am giving this signal. So, my VD2 is not 0, right. So, my VD2 is not 0. In that case, if I look at this, equation, my VD1 is 0, but my VD2 is not 0. The question is then what is the output here, right. So, what is the output that we want to see. So, this output will be the crosstalk. Or an estimate of the crosstalk, because nothing is given on this interconnect, but still I am receiving something. So, that is the crosstalk which is coming from the second interconnect. So, if I look at this, so if this is 0, my V crosstalk can simply be written like this, right. So, my V crosstalk is this term. Now, in the way we had written these expressions, a minus sign comes here. However, if we need to see like whether this crosstalk is really negative. So, let us look at this. So, what was your T D common mode? T D common mode was R C L square by 2, and your T D differential mode was C plus 2 C C into L square divided by 2. So, from here what we know is that your T D M is greater than T D common mode, right. So, then if I want to look at the how this would attenuate, so I can say that my T e to the power minus T divided by so this is a bigger term. So, this if I bring it this in the exponent, there would be a smaller term of e to the power minus. So, what I am saying is that my 1 by T D dm is then less than 1 by T D Cm. So, this term here, this term would be attenuating slower than this term here, and as a result what we will get is that your your e to the power, or say let me write it in this, e to the power minus T by T D Cm minus e to the power minus T divided by T D dm will be negative. So, overall what will happen is that your V cross is positive. Let us look at this in slightly more detail. So, if I want to write V So, I had this minus sign here. So, let me keep it for few steps. So, V d 2 into e to the power minus t divided by t d common mode, right. I have taken this out. So, if I take this out, I will have get term of minus t divided by t d differential mode divided by e to the power minus t divided by t d common mode, and then if I solve it further, I will get e to the power minus t divided by t d common mode into 1 minus e to the power minus t into 1 by t d d m minus 1 by t d c m, right. So, your t d d m minus t d c m would be r into so this will be r into c plus 2 c c L square divided by 2 minus r c L square by 2. So, this minus t d c m will be equal to r into c c L square, right. So, this is a positive term. So, if I then write V cross 1, so I will have V d 2 e to the power minus t divided by t d c m into, let me bring this plus here. So, this exponent I have brought it here. This is t into r c L square divided by t d dm t d cm minus 1. Now, if I do an expansion of this exponent, I will get as V d 2 e to the power minus t divided by t d cm into, so I will have 1 that will cancel out this with this one, plus t into r into c c into L square divided by t d dm t d cm and more terms and a minus 1. So, this minus 1 and 1 will cancel, and what you will get is that V. So, your V cross is actually proportional to, it depends on C c, not directly. I mean, if you take an approximation, it is there, plus some more higher orders of C c, but overall your coupling term gives you the crosstalk. If your coupling term goes to 0, your C c goes to 0, then your crosstalk will also go to 0 irrespective of V d 2. Similarly, if I look at the the voltage term only here, in the limit when my C c goes to 0, my differential mode and common mode delay would be the same, will be equal, and then this will reduce to a simple equation for an identical interconnect, whereas this will go to 0. Right. So, here with this analysis it tells us that this cross coupling is proportional to this coupling term. The more is the coupling term, more will be your induced voltage on the on the first interconnect because of the second interconnect. So, if I look at this nature, there is a t term here and then there is a exponent here which then decays out. If I look at my if I want to plot my output voltage, it will then look something like this. There will be this, the moment here there is a ripple, there will be something like this. So, this would be your crosstalk. So, this will be the ripple that is introduced. What this means is, if I am not giving any input to this first interconnect, and if I am giving a clock on the second interconnect, I can generate these type of ripples on the at the output of first interconnect if there is this coupling. Now, the another consequence of this coupling is timing jitter. So, here we saw that because of the voltage on one interconnect, you are getting a voltage which is induced on the second interconnect. This second effect is interesting in a way that now your interconnects do not just introduce a delay. Your delay is also dependent on the signal on the previous line. So, when there is coupling, the delay becomes a function of the signal on the adjacent line. We will see how. What this means is that your delay is not fixed, it depends on the data on the adjacent line. To understand this, again we are sticking with the case of identical interconnects and an oversimplistic scenario where the two pulses are synchronized. In that case, let us say that let TD1 be the time taken for the output to reach some voltage VTH. So, this VTH can be anything, it will not change the argument which we are making. So, if VTH is equal to 0.63 times the maximum value, then TD1 is your 63% delay. If VTH is 0.5 times of your maximum value, then your delay is 50% delay. However, you define this VTH, what you can do is that you have a now for this special case of identical interconnects, you have a nice closed form expression for your output voltage, right. So, you can solve this. So, your V out 1 of TD1 is equal to VTH. So, you solve this to get TD1. So, you will have an equation like this where now T is replaced by TD1 in all these terms. And if you look at this, you can see that your delay, your TD1, you have to solve this transcendental equation, is not just a function of. So, what all this TD1 is dependent on. So, this is dependent on TD common mode, TD difference mode, and this is dependent on the interconnect resistance, interconnect capacitance and the coupling capacitance. So, if this was the only dependent term, it would have been okay. I mean, you have interconnects which are coupled, there is some delay, interconnect is introducing a delay. However, to make the things worse, what is happening is you have a term of VD2 also here. So, here VTH will be in terms of VD1, so that can be taken care of. But what about VD2? So, if you solve this, you will see that your TD1 would be a function of not just R and C and CC, which are the interconnect parameters, but also a function of VD2. Depending on whether your VD2 is 0 or whether your VD2 is very high number, your delay would be varying. So, what it means is that your delay TD1 varies as a function of VD2. So, for example, your VD2 can be negative. I mean, you can, if your VD2 is say -1, it is a falling edge, right. So, in that case your delay would be this term would have different contribution, right. So, it becomes lot more complicated. So, if I am having so this is my say V out of 1 t and this is time. So, my signal is now not just having a delay, I am having different delays for different scenarios, right. So, my delay is varying. So, what I am getting is jitter. So, this is called the timing jitter. So, your output pulse has a delay. That delay is not fixed. There is a jitter in that time. So that's what is called the timing jitter. So this coupling also introduces a timing jitter, which is another undesired feature. So let us summarize what we have seen in this lecture. So in this lecture we derived the equations that give us an estimate of the crosstalk and timing jitters. We saw that crosstalk is proportional to your coupling capacitance. Then we saw that when there is a voltage transition on one interconnect, we get it sends voltage ripples on the adjacent interconnect as well. And then we discussed timing jitter. So interconnect delay is not just a function of interconnect parameters, it is also dependent on the voltage on the adjacent interconnect. In the next lecture, we will continue on our discussion on similar lines. So we will discuss the effects of coupling, timing jitter and crosstalk in slightly more detail. We will see where these become an issue. We will look at something interesting which is called the row hammer effect, which is a consequence of this coupling, and then we will look at some mitigation techniques. That's all for today. We will meet in the next lecture. Good day.